We're going to use these two simple circuits to talk about two really important rules. The first rule is about current. In a series circuit, just like the one here, the current throughout the entire thing is equal, which means that the current through this resistor, or through this resistor is all the same. This is really important because if you can find the current, then you know that it's the current through every resistor, and then you can use V equals IR to find the voltage drop across any of these resistors. And it's really easy to find that current. All you need to do is figure out what the equivalent resistance is by adding up each one of those resistors. Once you have that equivalent resistance, you can just do I equals V over R, where V is the voltage of the voltage source and R is the equivalent resistance. Whatever you get for that current is going to be equal to the current through each resistor. And again, that is what you would plug into these equations to figure out the voltage drop across each resistor. Now looking at the one on the right, this lets us see that anytime a circuit branches like what we have here, the current that enters that branch will be split up. So let's call the current that's entering that branch point right here I1, and then it gets split into I2 and I3. I1 is equal to the current of I2 plus I3. And if we follow I2, it will be the same through that entire piece of the circuit, and we can say the same through I3 up until the point that they rejoin. And then once they rejoin, the current that leaves that point is going to be equal to I1, which is the sum of I2 and I3. Now we're going to erase all this and look at the rules that we have for voltage. The most important rule about voltage is that the voltage drops in any loop in a circuit. So what I'm drawing here is this loop. The voltage drop, or delta V, across each one of these resistors, when you add those up, they have to be equal to the voltage source. And of course, the voltage source being the voltage of that battery. If we combine that with what we learned about the current, how the current is constant through any series circuit, and let's say we use that current to find the voltage drop for V1, the voltage drop for V2. If we know the voltage source, we can then use this equation to figure out delta V3. This rule really becomes important whenever you have parallel circuits like what we have on the right. Let's say that we have a 10-volt battery, and now let's trace our loops. This is one loop here, and this is a separate loop here. What that means is that the voltage drop across this resistor up here has to be equal to 10, because since that's one loop, the voltage drop across that entire loop has to be equal to the voltage source. And then we have to treat the red loop as a separate loop, which means that the voltage drop across that resistor also has to be equal to 10. What this shows us is that the voltage drop in parallel circuits is equal for each set of resistors that are in parallel. Now let's take all of this and look at a couple of harder examples. For these examples, first we're going to quickly look at how to find the equivalent resistor. When you do this, your goal is to get all of your resistors to be only all in series or only all in parallel with each other. If you see a resistor that looks like it's in parallel with two other resistors that are in series with each other, you need to get the two resistors that are in series with each other to look like one resistor. So first, let me add some values to all of these resistors so we can see how to do that. When you have two resistors that are in series, to find that equivalent resistor, all you do is add them up. That means that this equivalent resistor would just have a value of 5. I recommend that after you find the equivalent resistor, redraw the circuit with that inserted. For this circuit here, it would look like this. Once you get your circuit to have resistors that are only in parallel or only in series, you can use the rules that we talked about earlier to easily solve any missing values. First, let's use the loop rule that show that the voltage drop across resistors that are in parallel will be equal. Let's say that our battery here has a voltage of 10. If we look at our redrawn circuit, that means that the voltage drop across the resistor that has a value of 4 is going to be equal to 10, and the voltage drop across the 5 ohm resistor will also be equal to 10. That allows us to find the current through each one of these resistors really easily by doing I equals V over R. For this one, we have 10 over 5, which is equal to 2. And for the bottom one, we have 10 over 4, which is equal to 2.5. Then we can use the rule about how the current splits to figure out what the current going into that splitting point is. If we say that I1 split into I2 and I3, and we know that I2 is equal to 2 and I3 is equal to 2.5, then I1 is equal to 2 plus 2.5, which is 4.5 amps. Once you solve everything for your simplified circuit, go back to the original one and see what other missing values you can figure out now. In the original circuit, we can use that rule about how the current is constant through any series to figure out the voltage drop across our two original resistors. We used our simplified circuit to figure out that the current through those two resistors is equal to 2. So the current through this highlighted part of the circuit is 2 at all points. To find the voltage drop across those two resistors, you just do delta V is equal to IR. So for that first resistor, that will be 4, and for the second resistor, that will be 6. Lastly, as a final way to double check this, the voltage drop across each of these resistors should add up to be the voltage drop across the combined resistor that we used in our simplified circuit. If they do add up to that value, then that confirms that you did it right, and ours does add up because 4 plus 6 is equal to 10. Let's do a final example with the circuit on the right. For this one, it looks like we have a resistor that's in series with these two resistors, which are in parallel with each other. So like we said earlier, that can't work, and we have to combine these two resistors first. These two are very clearly just in parallel with each other, and to find the equivalent resistor for those two, we do 1 over the equivalent resistance is equal to 1 over 3 plus 1 over 4. To add those two fractions, we have to find the common denominator, which is 12, so we have 4 over 12 plus 3 over 12. That's 7 over 12, and then to find the equivalent resistance, we need to take the reciprocal of 7 over 12, so that equivalent resistance is equal to 12 over 7, which is equal to slightly below 2, so we'll say that that's roughly equal to 1.8. Now, as always, draw a new circuit with that equivalent resistance inserted in. Our new circuit has resistors that are only in series with each other, so we can start solving it now. Once again, let's say that our battery has a voltage of 10, and we're going to use this voltage to figure out what the current is through this circuit. Since everything is in series here, we just have to figure out what the current is through this whole circuit, and that will be the current through each individual resistor. To do that, we need to figure out what the equivalent resistance is for these two resistors. That equivalent resistance is equal to 3.8 since we just add up those two resistors. And then we easily find the current by doing I equals V over R, and we plug in 10 for V and 3.8 for R. That's going to give us a current that's a little bit below 3, and let's say it's about 2.8. Since that's the current through the whole circuit, we can use it to find the voltage drop across both resistors. For the first one, that is delta V is equal to 2 times 2.8. So delta V there is 5.6. Delta V for the second resistor is 1.8 times 2.8, and that comes out to be about 5. And remember that the voltage drops across both those resistors need to equal the voltage source, and 5.6 plus 5 is pretty close to 10, and remember that we did some rounding, so that's why we're off just a bit. Now we need to take everything that we did with our simple circuit and use it to help find any missing values in the original circuit. We know that the current leaving the battery and going up to this point was 2.8, so we're going to set I1 equal to 2.8. It then splits into what we will call I2 and I3. We don't know the values of I2 and I3, but what we can do is find the voltage drop across that resistor and the voltage drop across this resistor to then find those missing current values. Since we found the voltage drop across the equivalent resistor when we combine those two that are in parallel with each other, that voltage drop can then just be applied to each one, so they are both 5. And like always, we can double check this by looking at each individual loop and making sure that the voltage drops in each loop add up to 10, since 10 is the voltage of our battery. Remember that the voltage drop across the two resistor right here was equal to about 5.6. So for that green highlighted loop, we look at 5.6 plus 5, and that's pretty close to 10. It's a little off just because of rounding, but that does confirm that we've done everything correctly. And then for this red highlighted loop, we are again looking at this voltage and adding it with this voltage and hoping that it adds up to the voltage source. And once again, it's really close to 10, so that confirms we did it correctly. Now we can finally use the voltage drop across these resistors and the value of those resistors to find the current through each one. For the first one, we do I is equal to 5 over 3, and that's equal to about 1.66. And for the second one, we do I is equal to 5 over 4, which is equal to 1.25. The last thing we do is just confirm that we did those right, because I2 plus I3 need to equal I1, which was 2.8 amps, and our values that we found for those, which were 1.6 and 1.25, do add up to a value that's really close to 2.8. And again, it's just off because we've done some rounding throughout this process.